Hey guys, that's my real name. Most people struggle with that, so I chose Joe as my call name, kind of like slash. If you have any questions or you want to follow up on this talk, Twitter is probably the best place. Twitter or email. I'm based in New York. I spend most of my days building startups and consulting startups. And I do these sort of technical projects as a way to kind of have fun, I guess. So before we start talking about RPython itself, I want to do just a very quick introduction of what interpreters do in the first place, and then later what RPython does for you. So what is an interpreter? Of course, Python is not a compiled language. We never compile Python. You just pass it to some executable, and it runs. What actually happens? Well, an interpreter is three main parts. The first one, of course, it parses your source code. That's a part which is actually the easiest to do. We can do it super, super quickly, and there are loads of tools available. So most interpreters can do it in, I don't know, under 5 milliseconds. Just run through your source code, bam, done. The second part is that once you have parsed the source code, you have resulted in a little piece of kind of source code, but now it's called bytecode. So when you're running even normal Python code, you would have those PyC files. The PyC files contain bytecode. And the only thing we have to do with bytecode is to run it sequentially, run for every single command in the list, and the end result is whatever that program has produced. And then the last remaining part in now interpreter is you have to have some kind of a standard library. Most interpreters come with access to I/O or with access to networking. An interpreter without a standard library would be kind of useless because you would have access to no external sources. So if you look at actually the 4 steps of getting to bytecode and actually getting running, the first part is lexing. Your source code is just a string. It's just a string. You parse it to the token list. Done. Super quick. The next step is that most modern, both compilers and interpreters would generate a tree structure of your source code, usually referred to as an AST tree or an abstract source tree. We create a source tree as opposed to just having a flat structure because it helps us to reason with the way your code is structured. And then we can use a lot of tools to play with your source code programmatically. And then the last step before we run it is we generate bytecode. We take the source tree, we run it through some kind of a bytecode generator, get the final result, and then we can run it. And the running part is super easy. You just call eval on every single opcode, whatever way it's implemented, and you get the final result back. So when we're talking about bytecode, for me, it looks like an assembler code, just it's not actual assembler. So if you have a simple function like that, therefore you have 2 variables, that it returns a sum of the variables. Let's look at what it actually looks like in bytecode form. That's what our interpreter will use to actually run it. So luckily, Python has a library called dis, which stands for disassembler. So if you just disassemble this function, you get this back. If you've done any assembler of any sort, it kind of looks familiar. And what it actually contains is these 3 lines of source code represented in operations. And if you just kind of look at it, it's very obvious what it actually does. The first line loads a constant, so that's number 2. When it stores that in the variable with an index of 0. When we do a second constant, store it in a variable. Then we load those variables back. We do a binary sum, and then you return a value. That's what bytecode is. And this actually can be stored in the PyC files in a binary format and loaded anytime you need to run the program. So we don't have to do it repeatedly. We can just store it and save it. What interesting happens, though, is that you see the structure is a flat structure. So there's no any function calls. It's just a flat list of opcodes. So that was one of my first questions is, so how do you do a function call? Obviously, when you do a function call, now you jump through a different scope. So variables are different. You also should not be you should not have access anything in a parent scope if you've not defined that. So it gets really complicated and really interesting with function calls, because actually in a function call, anytime you want to call the function, it finds and fetches the bytecode of that function, something we saw before. Obviously creates a new scope of variables, and then runs that function almost as if it's a program by itself. That was like my big wow moment when I started doing this. It's like a function, running a function and running a program by itself is pretty much the same thing. Anytime you want to call a function, we build a new scope, we run the interpreter from 0 again, from a first position again. So it looks exactly like running a program. And that's why most programming languages will limit you how many function calls deep into the nested tree you can do. Because if you keep creating new frames, new scopes for variables, if you keep diving down and keep calling and calling in a nested function, eventually you run out of memory. So most programming languages limit you in the nestedness. So that's the basic of interpreters. The most important thing we've recently kind of invented is JIT. Pretty much any modern interpreter uses JIT. The old ones, the ones who've existed for a while, are not using JIT because it just takes too much effort to kind of get back to using JIT. But anything modern uses JIT. Both compiled languages like Java, who end up running on JVM, uses JIT, to PyPy, to both Ruby implementations, to PHP implementations, all sorts of different languages use JIT. The coolest thing about JIT is that instead of running through the list of opcodes and keep executing some level of, some list of machine codes for every single operation you have in the bytecode, we actually track what happens anytime your program runs. And then if we figure out some hot part of your application, some kind of a loop which gets called 1,000 times, we actually stop executing, compile that to machine code, and then continue running it. Which is actually the part which makes any interpreter with JIT probably as fast as just writing it in C, because as it runs, it optimizes itself. The bad part, though, these sort of things are super tricky to write, because you're not only writing an interpreter, you're also writing an interpreter which can stop at any point in time, figure out what happened as it was running these commands, and then optimize itself. And there are loads of ways to optimize that. The most obvious ones detect loops, detect function calls, which happen thousands and thousands of times, and figure out how to make them faster. Or if you have if statements, which always result to being true, just don't do if statements at all, just remove them altogether. It's pretty cool and pretty complicated. And this is how we get to RPython. So how many of you have seen this thing before? How many of you have heard of RPython before? So I guess most people. So PyPy uses RPython. It used to be a hidden part of PyPy. It used to be kind of unavailable for anyone outside of PyPy, but now it's actually morphing slowly and deeply into being a self-contained project. So what is RPython? So first of all, it's a language. RPython looks like Python, and you can actually run it as Python, but it has removed all the slow parts, which means we can compile it down to C code and make it really, really quick. Second of all, because there's this whole tool chain involved of compiling our Python to C code, of course, we no longer have access to the standard library. So RPython also comes with its own standard library, rlib, which has a set of libraries. So that's kind of a limitation of writing anything with RPython, is that you no longer have access to the standard tools you've had before. So while it kind of looks like Python, not everything is available. But the best thing for us is that we can write interpreters in it, and it also has JIT just in it, and also does garbage collection for us. So instead of writing thousands of lines of code, of C usually, to write an interpreter, we can all write it in Python, throw a little bit of our Python-specific function calls, and all of a sudden we have a JIT interpreter. The way it can be described, and this is a pretty complicated graph, but basically the way it works is you start from RPython source code, which kind of looks like Python. You build a flow graph, which means you look at what is being called with what arguments, and you figure out what types are being used. And once you know what types are being used, you can also validate that any single function never gets called with a different set of types. And if you can validate that the types are always the same, you can remove every single type checking in there. You can compile it down to just pure variables, like pure to low-level sense. And then once you have generated that, you can generate C code, or you can generate LLVM code, or any sort of output from there. In most standard setups, you end up generating C code, which kind of in the background ends up getting compiled, and then you have an executable out of it. RPython is actually really, really quick. So, of course, PyPy makes Python really quick, but actually RPython by itself is an incredibly quick thing. Because it does type analysis and because it figures out and removes all the slow parts, it's probably as fast as any sort of C code you would write. There are examples of writing Fibonacci algorithms in RPython, and once you compile them, they're actually faster than C would be. It's just the advantages of doing like very complicated type analysis and flow analysis and removing all the slow parts and removing all the unused parts. So it's super, super quick once compiled, yet you can actually run it as normal Python programs. And that was a big thing for me because I was like, I want to learn how interpreters work, but I don't feel like writing one in C. Because even to get started, it would take so much time and so much effort. And if something breaks, I have no idea why it's broken. In this case, I'm writing everything in Python. I can run it as Python, but once I want to make it kind of production ready, I just compile it, and now it's fast. Huge thing. So it has these type checking things. So to start, it would never allow you to use two different types on the same variable. While this is valid Python code, it's invalid RPython code, because you're redefining variable types. And while in this case, it kind of looks almost wrong, because why wouldn't it allow you to redefine variable types? Once you do function calls, it wants you to make sure that variable types are always the same. Second of all, it would never allow you to refer to a variable expecting to be a certain value, even though there's no proof that it will be. So in this case, x, in some cases, might be none, but you're assuming it's always going to be an int. So once it does its type analysis and flow analysis, it will actually figure out that this actually is invalid code, because it will fail certain conditions and will simply not allow you to compile the code. And it gets deeper and deeper. So when it comes to inheritance, in my method here, I'm referring to a property of an object, and I actually have to have an assert statement, which is actually missing an A in front. I have to have an assert statement because I'm just saying, hey, not only I expect this instance to be a child A, I actually know it to be of child A. So asserts in RPython are actually hints to the compiler saying, hey, I wrote this code, I know it has to be this type of variable. And because these classes are sharing a same parent, RPython by itself cannot guarantee that this method will always be called with child A and not child B, which would not have that property. So it does a lot of these strict enforcements of your code, and that's just one of the ways how it makes it really quick, because it never has to check for something existing after it has compiled it, because it has validated that something will always exist, something will always be of the same type. For Jet, it does these optimizations of, basically, in this object, you're defining that my sum class instance will always have these two arguments and two properties of an actual object, and they will never change. So basically, you're saying, once I have initialized this object, these variables will never change, which means anytime you refer back to those properties of an instance, RPython doesn't have to check if they exist, doesn't have to do anything like that. It can just assume they exist. In most of the cases, it will actually put those variables into the heap structure because it will know they will never change, so we can safely store them. This alone will make most of the programs really, really quick because it removes checking for things existing. We always know they're going to exist. And the last variable, the reason why it has these like square brackets and a star, is because we were saying the args variable is actually a list which elements are not going to change. vicious optimization hints. And then the last bit, and there's many more, is in this case, we're just saying anytime you call this lookup function, it's actually a deterministic function. And with the same arguments, it will always return the same value. And you can kind of implement that with like some kind of a memorization decorator. But in this case, we're doing it on the kind of compiler level. What we're saying is, anytime you call this, the result is going to be the same. So once you call it once, just store it and remember it forever. Because if you think about most of the programs are some kind of dictionary lookups. Anytime you look up a variable, it has to find that variable somewhere stored. Every time you want to store a variable, again, it has to find where it is. So there's a lot of dictionary lookups. By defining the non-changing dictionary positions, the code becomes super quick. So what is working with RPython? You keep writing normal Python, and once you have your program working, you try to compile it with RPython, it fails, and then you spend the next 7 weeks trying to make it not fail. And I'll come back to this, but when you saw these like immutable hints and elidables and type systems, it's a very complicated thing. So once it tries to kind of find all the flaws you had in your code, it will take a long time, and then it will fail with somewhat cryptic errors. So a big part of writing RPython is kind of learning what errors mean, and then trying to make those types conform. So this is stupidly what I decided to do. I was like, I want to learn how interpreters work. I want to learn what RPython is, but how do I actually do it? So I was like, okay, I'm going to build an interpreter. So that's exactly what I did. It's called PyHP, and it actually is a working PHP interpreter written in RPython. It's all available on GitHub. It's barely a couple thousand lines of code, loads of tests as well. What does it actually do? Well, it implements basic PHP functionality. It doesn't do classes. It doesn't do a lot of these things, and I'll come back to why in a second. It has like a little HTTP server in it, so you can kind of run a script, and it has like a RPython built HTTP server, so you can serve your scripts online. It has unit tests, so most of the functionality is actually tested, and you can run them as a Python test suite, so nothing is specific to RPython. And once you run it through a JIT compiler, it's super quick, incredibly quick. And I got to this point by basically finding a GitHub source of some kind of a Lisp interpreter written in RPython and modifying it to work with PHP, as you do. A big part of it is, of course, defining a grammar. When I was saying how like parsing source code for most of our programs is pretty quick and we can do it very quickly, it's because in most of the programming languages, you have a file which defines the grammar in some kind of a textual form. It's a bunch of regular expressions and a bunch of like nested statements. And then you can take this file, feed it to a parser generator, and it will generate an actual parser. So in this case, this is just a sample of what PHP language would have. So you have a variable which starts with a $, and then a bunch of letters or numbers, and then you can have statements, and you can have if statements, and you can see how it kind of all adds together. We will feed this later to a generator, and we will get a parser. It also has data types. So because we're writing Python, of course, every variable is represented by an instance of an object. So in this case, I have a Boolean data type. The value itself, the value of it never changes. So it's an immutable variable. It has a bunch of helper methods, like you convert it into a string. You can check if it's true or not. And we will be passing around this instance for our interpreter. But once it actually is, once it's actually trying to run it fast, in most of the cases, it will actually unpack this variable. RPython itself will unpack this variable and only just store the Boolean value in memory, because it doesn't need to actually store the instance. It will just store the variable because it realizes that all these variable types are just wrapping a simple type. And since it's just Python, it has a bunch of tests, like really, really simple tests, where all I'm saying is, here's like a bunch of PHP code, try to run it and just check the output. So I've done this kind of a test-driven development for this, where I just wrote down a bunch of snippets of PHP code, fed it to my interpreter, and just kept hacking on it until it worked. and tests some basic things like passing variables by value or passing by reference, which is a pretty complicated piece. And it has in the bottom here on the left, it checks that the stack never overflows. So basically just generates a program which is just 20 variable assignments. And if you did something wrong, it will actually crash. But if it actually works fine, then the test will just pass. And if you actually want to run it, you can just pull a container which has an RPython and PyPy installed in it. You build the actual executable you would run later, and then you just run the bench script. And the bench script is a very interesting part. So PHP comes with this bench PHP file, which tests a bunch of very simplistic micro-optimization level features. It's basically the language level test. This is PHP 7, the latest version. It takes 1.1 second to execute that. And this is PyHP. It takes 0.3 seconds to execute it. So it's almost 4 times as fast. PHP 7 also came out a couple of months ago, so before it came out, PyHP was probably 7 or 8 times as fast as the fastest PHP you would run. And that's mostly thanks to RPython and RPython bundling JIT in it. So I was able to write my normal PHP code, my normal Python code, and once I've kind of run it through a JIT, I ended up having this super, super quick library. Of course, it's micro-optimizations, the I/O is not necessarily faster, but it's pretty cool. And then I was giving a talk, and someone was like, oh, wait a second, PHP is not actually Unicode. So maybe, do you want to try to make PyHP Unicode, because Python is Unicode? Anyway, I was like, oh, I'm going to check that. And as you can see, it took me changing 13 files and a total of less than 300 lines. And all of a sudden, my interpreter was fully Unicode. So I went from just having strings to having everything in Unicode, variable names, actual strings, function names, everything was Unicode. And that's just thanks to because everything is actually Python code. So I just changed the variables I was using to Unicode strings, and all of a sudden, everything became Unicode. And once it's compiled, it's still really quick. It has all these advantages, but because I'm just playing around with a bunch of Python code, supporting things like Unicode is just a matter of 13 changes. Then there's issues. Nothing is documented, not a single part. So anytime you get an error, you Google for it, and it says, oh, did you mean something else? Because there is 0 results. That was a big issue and a massive time suck, because anytime something fails, you have no idea why it failed, and there's no information why it failed. The documentation now is growing, but it's still not there. I ended up looking through RPython source code most of the times, because you just search for what part of RPython is generating this exception and try to figure out what it actually meant. Especially the JIT errors, once you kind of run your interpreter compilation, and 15 minutes in, it's oh, by the way, it doesn't compile because of this, and you have no idea what you have actually done wrong. So I was trying to make sure, anytime I change any sort of significant part, I'm always committing the code, and I'm also always running the build, so it's testing. Because once you go too deep, and you for example, ran a week without trying to compile that, it will start failing in the ways which you will never figure out why. So most of my development was, let's build a new feature. It fails to compile. Let's roll back to the previous version, make sure it actually worked, and then try to figure out what was wrong. So that was a big deal. And then lessons learned. The reason why it doesn't support classes is because it's just a matter of time. So once you have most of the basics in, it's just a matter of time. So supporting standard library features, which PHP happens to have a lot, is just a matter of implementing them in Python. Most of interpreters end up having to re-implement everything again, because you can't just access things from external systems, easily at least. So that was a big time suck. So I chose not to support classes just because I didn't want to spend any more time on this, and I just chose to support the most basic things. Some PHP-specific things are just, I still have no idea how to implement that. For example, PHP has a feature called eval, which takes any string of valid PHP code and actually executes that. I have no idea how to actually implement that, because that means my interpreter has to be bundled with the runtime. So as it's running the code, it's also parsing some new code, which I have no idea how to do that. And function calls are expensive. So anytime you call a function, I have to build a new frame, a new scope of variables, Those variables sometimes can access the parent scope, sometimes cannot access the parent scope. There's also references involved. There's complicated data structures involved, like lists. Like, so what does have access to what? That was a big time suck. So optimizing things like Fibonacci, which is just a massive recursive function, was an interesting challenge. But actually, one of the tests in the bench file is a Fibonacci generator, which, as you know, just keeps calling the recursive function many, many times. So trying to make it fast was a very interesting challenge. So if you want to start this yourself, where do you start? Probably you shouldn't start, but if you actually still decide to start that, this is where you would start. So any RPython program starts with defining an entry point. To this day, I haven't found any documentation of what the second argument is for, or what it actually means. But from running it, I know just you have to have a tuple of two variables. The first one is the entry point. So basically, when your compiler runs, it will call the entry point. Like once your program is compiled, once you run it, it will go through the entry point. So the target is just instructing the compilation process. The entry point is what actually we're going to get called. So if you want to expand that, our entry point probably looks something like this. The first argument is a file name, so you can do some simple checks. Let's just check it's an actual file, try to read that file. And then you parse the source code to an AST tree, something we looked at before. Then you compile that to bytecode, and then you get from somewhere an interpreter instance, and then you run it. And then you just return the status code of 0. So an entry point is not the one which is actually like printing things to send it in and out. But our interpreter is doing that. An entry point, if it doesn't fail, just returns 0 as a normal Unix program. So let's start parsing. So when I was showing our grammar file, luckily, our Python is built for these sort of things. So it has an EBNF parser in it. So all you have to do is just parse that file, pass that file into it. It will read through it, and it will basically build us a parser. That's not the only way to build parsers, but that's probably the fastest way. Because all you have to do is create this grammar file. You pass a bunch of, you pass it, and then you get a bunch of kind of instances and functions you can use to actually parse the source code. Then you take the next step. You want to kind of transform the internal structures of RPython to something you would want to use yourself. So you build a transformer, which is just a visitor pattern, which for any part of our grammar file, it will call with any nodes inside of it. So you see, when I'm building an if statement, I'm just checking how many children it has, and based on how many children it has, it either has an else block or it doesn't have an else block, and out of it, I build these operations. And as I build up more and more of these operations, eventually, I will get an AST tree of operations nested into each other. That's it. Like once you run this thing, you have an AST tree out of it. Then it gets to bytecode. Once you have an AST tree, all I have to do is call compile on every single node of it, and it will actually just append a tiny opcode to a list of bytecodes. So the bytecode instance at the bottom is the one which gets passed to every single compile method, and that compile method will just keep appending opcodes. And in this case, you will see that it will, whatever was following print, it will compile that. So basically that, if it's just a variable, it will return that variable first, and then this print will run. So the first AST is probably the source code itself, like AST for source code itself, and then it goes through a nested or kind of a recursive function call of just keep calling what's inside of it. And eventually it will build a massive list of bytecode. Very, very simple. And then we're finishing the last step, is once you have a bytecode, and I'm kind of slowly running through these slides because they'll all be available online, so it's going to be easier just to look at it yourself. Once you've reached the interpreter stage, that's the simplest part. Well, it's not simple. If you look at this 30 lines of code, in CPython, I checked this yesterday, is 2,000 lines of code. Luckily for us, it's just 30 lines of code. And you will see what it is. It first creates a frame, so it's just a place to store variables and a place to remember what's being stored in variables. And then it just runs through every single command in the bytecode, for every single opcode in the bytecode, in a list, starting from 0 all the way to the end of it. And it just expects it to do something. So if it's a print statement, it's the opcode which is actually going to print something. If the opcode is a return statement, it will get whatever is currently on the stack, return it back to us. If it's some kind of a jump, then we just set the new position to it, and then we jump out of it. Like, that's all involved in actually running our opcodes. Because every single opcode itself implements the kind of the machine level things it has to do, the VM level things it has to do. And if we decide to add JIT support, like if we decide to actually make this part fast, all we have to do is add these 3 statements. And that's kind of getting to specifics of how JIT interpreters work. The first part is obviously defining the driver. The red and green variables is a way to tell the interpreter saying, all the green variables do not change in the single execution loop. The red variables change in the single execution loop. Because our bytecode, of course, never changes, our position statement, the PC variable, never changes outside of a single iteration. They're green variables. The frame, the object which stores all the variables, of course changes because the opcodes will be changing it. So we're just telling it's a red variable. And then all we have to instruct is where does the single loop of interpretation start, and anytime you want to run backwards, so anytime our position is actually jumping back in an interpretation list, you just have to tell it about that as well. For both of these, not 100% sure how exactly does that actually work. All I know is with the first one is that the interpreter knows if it decides to jump back, for example, if it decides to compile your code to machine code and if something fails, it knows at what position it can fall back to. Why do you have to tell it if it ever wants to go back in terms of execution? Not entirely sure. I don't know. Try to find it, no idea how it works. So I just found an example which worked, and I did it. That's how most things work. And then that's it. All you have to do is to compile it. So you run this command, and in this case, it has all the optimizations disabled, which is probably something you would do most of the time. That's the quickest way to compile it. Would probably take less than 5 minutes, and the end result, is an actual executable you can run. It compiles for whatever operating system or whatever 64, 32-bit system you're running it. So you would have to compile it on different systems if you want to be accessed by, if you want to like send it or share that file to someone else. And if you want to compile it with JIT, then all you have to do is just pass opt JIT. This probably takes at least 5 minutes because it's much, much more involved, and it's basically generating a JIT compiler anytime you run it. This will probably fail, so you will just keep running it and it will keep trying to make it work. Once you have compiled this, once you have the final executable, there are interesting challenges is how to make it actually fast. So achieving that like big performance difference I had showed in the slides, it didn't come just by running it. Of course, there is much more involved. So what you do is you can do a PyPy log file. And you can use this both when you're running your own programs, your own interpreters, or if you're just using PyPy. By outputting a JIT log file, it will actually tell you every single thing it does. And every time it decides to compile machine code, every time it tries to access some kind of a variable and it's not available, all these sort of things, it just spits everything out. Then you can also, if you want to, then you can also show that as a graph. And if you keep doing this for long enough, if you keep running through this loop, you will eventually find the slow parts. You will find variables which can actually be flagged as immutable, so they will never change, so don't try to bother checking for them. and you just keep running that. So there's a bunch of resources. Actually, the best part, the best place to look is the More PyPy blog. It talks about everything PyPy, and it's where all the announcements happen, but it also has very good bits about how RPython works. Then there are some RPython docs, pretty high level, talks about the basics, talks about the structure of RPython, talks about fundamentals of it. A pretty good project to start looking is the actual Ruby compiler. It's probably the biggest RPython project outside of PyPy. Or you can look at my later project. Let's grab a glass. There's one more thing. So when I had in the slides this example of how it's computing flowcharts and it's computing types, in the rightmost corner, it was saying that the final result does not have to be C code. It does not have to be C code which ends up getting compiled. It can also be LLVM code. Or it can be something else, like JavaScript. So this is not actually a joke. It's a real thing. It's even more real for PyPy. So first of all, it started off from PyPy.js. You can actually run PyPy in the browser. It works. Everything works. It even supports different Python versions. I've also done the same thing. And the way this achieves that is that instead of our RPython code being compiled to C code, it generates the C code, and then it passes that to mscripton, which is an open source library which generates JavaScript out of any C code. And then the final result is like 25 megabytes of JavaScript, which will actually run the same thing that we had before. And the interesting and the kind of a mind-blowing thing about these sort of things is that it's not emulating anything. It's not transpiling my PHP, or in your case, Python code to JavaScript. It's an actual VM in JavaScript which runs everything natively, in a sense. It does its own output buffering, it does its own garbage collection, it does all these crazy things in JavaScript. Does anyone have any questions? What's that? The JavaScript part? So, I don't know if I had internet. Wait. So I don't know if I have it on my laptop here compiled, I think, but I have a visual example. So this is, remember how I showed the benchmark? And I did it at 0.3 seconds. This is doing the same thing in 24 seconds. And the interesting part of it is that that PyHP VM.js file is generated from the same source as my really, really fast JIT compiler. It's running through Node and doing the same thing. I don't know anything of why it's much more slower, because V8 and Node has to be pretty quick, but it actually works. And I didn't have to change anything at all. It's doing its own print statements, it's doing its own output buffering, it's doing its own memory allocations, just in all JavaScript. Yeah.
Two quick questions. First, is there tooling available yet to help with that Python to RPython transition, or is that still mostly, as you said, run it, it crashes?
Yeah. It's, yeah.
Is that? And secondly, it seemed as though from what I could tell, the parser part is pretty loosely coupled to the rest of it, and so it doesn't seem that it would be particularly hard to swap a new parser module in.
Yeah.
You just have to produce the same data structures, right?
Yes. Okay. So RPython has a few libraries which kind of help you. So you can do like a decorative approach of defining a parser. You can do the approach I had, which is just based on a grammar file. But the end result is your own internal functions. So the final result of operations if was actually my object. So it was something I did. So you can then put it to any other part, and it will still work. So everything is pretty pluggable. The final result, which is like, hey, here's a bunch of bytecode, let me run it. That's a part which doesn't really have a lot of flexibility. The way you come up with that, so for example, I was like, oh, let me implement a bytecode cache. It's just kind of up to you. Like you just store it in a file somewhere. It's just normal Python code. So some people claim that instead of RPython trying to generate this pretty much optimized C code, instead RPython should generate these LLVM-ready data structures and then pass it to LLVM to generate the final C code, basically. So it's basically an assumption that LLVM would do a better job at generating this low-level code, which I don't know if it has been proven to be either though. Like, is it actually true or not? I don't know. But basically, instead of generating C code and passing it to LLVM, it would generate LLVM data structures and pass it to LLVM, and then use LLVM to generate machine code. Because LLVM is not Python specific too, so it has so much knowledge built into it that a lot of people would say it could probably do a better job at generating low-level code. I don't know. I don't think it's actually the default target. I'm pretty sure it's not. Any more questions? Yeah, the standard way generates C code and then just passes that to a GCC compiler and then compiles that. It would take too long, but I could actually run it here on a stage. And you will see that the final result is just a bunch of C source code file. So it translates RPython itself, then it translates my little addition to that, links everything together, and compiles it as a single executable. And I think the final result for PyHP is just like a 9 megabyte executable file, which both obviously has all the RPython libraries and all the other stuff in it and my code. Any more questions? So I will share those slides online, and I guess on Twitter as well. So it's going to be much more easier to follow the code if you just did it yourself. And then thank you for your time. And if you have any more questions, you could tweet or find me here. Thank you.